Welcome to the fifth, I believe, lecture in the series on input and output. In this video, we'll be talking about compressed files, particularly files that are compressed using GZip. Now, you're probably familiar with file compression, and those of you who have worked with Windows or Mac have probably encountered zip files many times. Zip is a very common compression format. GZip is another common compressed file format, closely related to zip, but more commonly used in the world of Linux and in the world of computer programming and in data science. So we'll be working with gzipped files quite a bit. And just like zip files end usually in an extension of zip, gzip files usually end with a file extension .gz. So why do we want to compress files? Working with files, as with anything in programming, uses resources. Storing files on disk costs us storage space. Sending files to other people over the internet uses network bandwidth, which also uses our time. So to speed up downloading files or uploading files, as well as to reduce the amount of space they use on disk, we compress them. File compression relies on the fact that data often contains patterns. And by representing the data using its patterns rather than every single element of the data, we can reduce the amount of space that we need for that representation. In some instances, that representation may compromise the integrity of the data to some degree. For example, for audio files or image files or video files, it's very common to use what's called lossy compression, in which certain elements of the data that we're not sensitive to as viewers or listeners are removed from the file to reduce its size. We're talking about something different. We're talking about what's called lossless compression, where we simply use patterns found in the file and an alternative representation of the file via those patterns to reduce the file size. One example is considering the list of the following numbers. We have 3 10s and then a 2 and then several 3s, some 50s, 1s, a 50, and then several 10s again. 18 integers in all. Rather than representing them with the full 18 integers, we could reduce the number of numbers we have to write to only 14 by instead saying how many repetitions of each number there are. So initially we have 3 10s, saving one number. We have 1 2, which costs us an additional one number. 5 3s, which saves us 3 numbers. 2 50s, 2 1s, 1 50, and 4 10s. At the end of the day, we've spent 2 additional numbers, but we've saved 6 numbers. So we've gone from 18 down to only 14 numbers in this representation. The longer this string would get and the more repetitions we would have, the more efficiently we could compress this list of numbers in its representation. Many forms of lossless compression use a very similar idea to this, although the actual implementations are somewhat more complicated. GZip uses what's called the deflate algorithm, which you can read about here, linked from this notebook. But the idea is it looks for repeated patterns in the text of a file and does a very similar kind of representation where instead of saying how many repetitions there are, it points to the last appearance of a particular pattern and the length of the match with that pattern. I'm not going to get more into how the algorithm works since this is not a course on file compression, but you can read about it more here. We're simply interested in how to work with such files. So I'm going to download a copy of the Epic of Gilgamesh from archive.org. If we actually go to this link, we see it's the full text of the Epic of Gilgamesh. And we'll be taking this as an example of a file that we could compress. To work with GZip files, we will be using the GZip module from the Python standard library. To read in this file that we just downloaded, to read in the text, we'll open it up as we saw previously and read it in. To write a compressed version of the file, we'll open a file using the GZip module for writing. It's important to note that compressed files are not simple text files. They are binary files. Therefore, instead of opening with just the W flag, I'll open it with the B flag as well. B stands for binary. And this lets Python know that I'm not writing a simple text file, I'm writing a binary file. Once I've opened this file using the GZip module, I can simply write the text as normal. Here I've included this encode simply because this text contains non-ASCII characters. So it contains characters in the text which are not represented in the ASCII character set. This encode has nothing to do with GZip. It simply has to do with the characters that are in this text. So once we've written the file, we can look at the files on disk and compare their sizes. The raw text file is 162 kilobytes. The compressed version is 46 kilobytes, less than 1/3 as big, almost only a quarter as large. So we were able to compress the file down to about 25% of its original size using patterns in the language. And this works really well for things like books, because language contains many patterns. And so there's many patterns to leverage in compressing the file. But what if we scrambled together all the letters in the text? What if we randomized the text? Then there would be less patterns for us to rely on in compressing the file. So I'm going to use NumPy to permute, meaning switch around, the letters in the text. And I'll write this scrambled version of the story to a GZip compressed file. The scrambled version still takes up less space than the original, but it's much larger than the original compressed version. So compression won't perform very well on random data. And this is somewhat important for when we're working with data ourselves. If we're working with a data table, if many of the elements of that table repeat, for instance, if they are names of people or locations, we might have many entries in our table with those same names repeated, in which case compression might help us a good deal. But if that table, for instance, has readings from some voltage sensor or a temperature sensor or something like that, the numbers might be almost random. So we might do a little bit less well when we're compressing data of that type. However, we'll still see probably some benefit even when the data is relatively random by compressing it. And so you'll see many of the data files we provide for the mini projects are compressed. So for instance, in the PW mini project, we have you download some GZip JSON files. So those files are compressed using GZip compression. Compression likewise does not work on data that's very small to begin with. And the reason, again, is because small data can't contain many patterns. There's not many patterns to be found in the word hello, because there's simply not enough characters to compare to each other. In fact, in this case, the original file is so small that the compressed version is even bigger than the original text. That's because compression carries with it a certain amount of overhead. A compressed file includes a header, which takes up some extra space. That header contains metadata about the contents of the file. In fact, if we try to inspect the contents of the file, we can see that header, which includes the file name and some other information about the file. We can't really read more than that because, again, this is not a plain text file. This is a binary file. So very little of this file is readable as text. That concludes our discussion of compressed files and file compression. In the next and final video in this series, we'll be talking about some file formats that are unique to Python.